view it. Okay, so the other day I started talking about this problem here, right? And so I said I got a voltage source, a resistor, and an inductor, and we went through the impedances of all of these things, right? So the impedance relationship we said is basically if I looked at, let's say, the voltage across an inductor, what's the impedance of an inductor? J omega L, right? Now, you never saw inductors probably in electronics, right? Reason for that is because on chips, they never have inductors, almost never have inductors, okay? But we have inductive loads a lot when we're talking about power devices because most of our motors and things have inductors. They're basically iron with copper windings. That makes them inductive, okay? So J omega L, what's the other way of thinking about that? That's basically having it in like real plus J imaginary form, right? What's the other way I can write a complex number? Omega L angle 90 degrees. Yeah, that's exactly right. Okay. What's that tell me? If it's angle 90, then that's the angle between what and what? What? The current and the voltage, right? So we walked through that the other day, right? So if I take V equals I times Z, right? That's basically what? That's the angle of, so V equals I times Z like that. What's true about the angles of those three things? What? Yeah, exactly. So angle of V would be the angle of I plus 90 degrees in this case, okay? So in that case, who's leading and who's lagging? Voltage leads because he's 90 degrees ahead of the current, right? I have to add 90 degrees to the angle of the current to get the angle of the voltage. So we would say that it's leading, okay? All right. I did start recording, right? I did. All right. Now, last time I talked about this and said, okay, if I did Ohm's law and KVL, I would get this differential equation for this whole thing, right? So again, I don't want to spend too much time on differential equations. We will use them a little bit because our motors, we got to worry about starting up motors and things like that later on. And those are transient behaviors when I start something, right? So if I said to you, what is the solution to this thing? It will have two pieces. Right? The solution would be I of t equals something. What would the two pieces of that solution be? There's a steady state and a transient, right? What's the transient look like? Mathematically, what's it look like? It's an exponential, and it's an exponential that always does what? What's that? Yeah, so it's always going to decrease over time, right? It's always going to decay. All right. And we don't know how big it is to start with. So I write it as there's this unknown value A in the front of it. If I looked at this problem in particular, tau would be L over R, right? I don't want to get into the weeds of that too much, but tau would be L over R, right? So I have this plus, what does the steady state response look like? Now, last time I talked about this problem, I introduced it. I said V of t is 9 cosine 2 pi 100 t. That's what we're going to use for this guy. All right. How would I write for this what the current looks like in steady state at this point in time? I don't know. I mean, I don't know what the amplitudes and all that stuff is, but what is it in general? Yeah. So whatever the peak value is times the cosine of what in particular? 2 pi 100 t. So my omega is 2 pi 100, right? And then I have plus whatever the angle of I is, the phase of it, right? So I don't know what the phase is. I don't know what the current is. Okay. So my approach to these problems is, let's say, so I can look at those two things separately. I can look at the steady state and I can look at the transient. I do have one problem in the homework problem too, where I ask you to do the total solution. All right. The easy one for me to do is to do this guy right here, right? How do I do the steady state solution? What's the easiest approach to doing the steady state solution? You know how to do it, but it sounds fancy when I ask it this way. If somebody asked you to find the current in that circuit, what would you do? You go to the frequency domain, so you go to do phasor analysis, and you would use the impedances, right? Impedances only apply in steady state. They don't apply all the time. They only apply in steady state. So how would I solve in this case? Forget the differential equation exists, right? So I've got v of t equals 9 cosine 2 pi 100t like that. I want to convert this thing into the frequency domain, right? Or the phasor domain, whatever you want to call it. So I'd be solving for the phasor for I. How would I solve for the phasor of I? How would I do that given this circuit? Voltage divided by the impedance, right? I have a series impedance. I got a resistor in series with an inductor, and I got a voltage source, right? So I'd say it's whatever the voltage phasor is divided by, what would it be in this case? Yep, PR plus J omega L. And I've given what the L is, right? Omega is 2 pi 100, right? So I'd plug all that stuff in there, right? And I would do the calculation. Now, one thing I said about the phasors that I use in this class, right? What would my phasor be for the voltage V? 9 angle 0 is what is a good guess. What I said the other day, that's why I wanted to, so it's 9 over square root of 2, because we usually use RMS for it, right? So 9 over square root of 2 with an angle of 0 degrees, though, because it's just a straight up cosine, okay? So if I solve that, if I plug everything in here, the important thing is, so it'd be 9 over square root of 2, angle 0, and that would be 100 plus J, oh, so what's my omega for that? 2 pi 100, right? So 2 pi 100 times whatever L is. I don't feel like writing it, so I can call it L, right? So you do the math on that. That would have a magnitude and an angle. You should know how to do that. Chances are a lot of you guys would probably put it in the calculator or MATLAB or whatever, right? And what would I get for this? What I get when I do the math is that this works out to 0.0283, sorry, 285. Not that it matters much. With an angle of negative 63.43 degrees. Okay. All right. So let's say I wanted to draw what the phasor diagram looks like. What would that look like? So the phasor diagram, not something we think about too much, probably. But so the phasor diagram would be, where's the voltage and current phasors? So where would the voltage phasor be in this case? Yeah, be purely on the real axis, point in this direction, right? 9 over square root of 2 would be its magnitude, and its angle would be 0 degrees. This would be V. Where would I be? Yeah, it'd be over here in the fourth quadrant, right? And I'm exaggerating his size. Current I is usually way smaller than V in any of these problems, right? We're usually going to have voltages that are like 120, and we're going to have currents that are like 1. All right. So oftentimes there's a big difference between the size of the two, but it would be like that. There'd be a 60. So is this guy lagging or leading? I. Which one leads? Which one lags? Voltage leads, right? Because he's more positive, right? This guy is 63 degrees behind the voltage. So you always look at which one is behind in that phasor domain. So if I were to say to you, what would the time domain waveform be? So the steady state, that's what I wanted to get, was what's the steady state? I'm going to call that ISS, I guess, of T. What would be the steady state time domain solution? In other words, if I go to an oscilloscope, I don't see, an arrow, right? With an oscilloscope, I see something that goes along in time. What's that going to look like on the oscilloscope in steady state?
You just convert that phasor back into a
Okay, yeah, so how do I do that? What's that going to be?
The magnitude comes in front and the angle that goes inside with the same frequency.
So what's the magnitude in this case?
0.02.
That's RMS, right?
Oh my God.
So 0.028, so we said our phasors are all going to be RMS. But if I'm writing the time domain waveform, the peak value has to be what's in front because it's the amplitude, right? So if you do the peak value of this, it works out to be 0.0403. How did I get that from 0.0285? Square root of 2, right? So cosine 2 pi 100t minus 61.43 degrees. Like that. Okay. So
Multiplied by square root of pi, 2, right?
this is a peak value that I put in front of that, right? So yeah, the peak value is square root of 2 times the RMS value. The RMS value is the peak divided by square root of 2. Yeah. Okay. All right. So if I drew those two things, which one, where would so if I drew the voltage would be like this, right? Be cosine, right? What would the current look like? Where would its peak be? Would its peak be before t equals 0? Or would it be after t equals 0? After. It's lagging. Its peak happens later in time. It's a little bit confusing sometimes. I of t would be peaking later, right? Why this is later, right? This is t equal to 0. This is, I don't know, t equal to 1 second or something. Probably t equals 1 millisecond or something. All right. This is a later time. That's what it means for it to lag. It reaches its peak at a later time, right? Lagging. Yeah.
So you talk about time,
What do you mean use the second quadrant?
when you're going with the leading value, so I was watching the video there, the median and,
Well, I mean, so stuff, I'm not quite sure if I know what you're asking, but sometimes stuff will be in these quadrants.
yeah.
But the angles of the impedances are only ever going to be in the first and the fourth quadrant. All right, so we'll get, I think I know what you're asking, but the angles of the impedances that you deal with better always be here and here. Now, if your voltage was over here, then your current would be somewhere over there too, right? But we typically don't give you a voltage with an angle of 300 degrees, or usually we give a voltage with an angle of 0 or something like that, right? All right. So now if I looked at this, if I went to an oscilloscope and looked at it, I would see this, right? So I get a transient plus a steady state. Where would I go to measure that phase shift? If I asked you to go to an oscilloscope and measure that phase shift is real, how would I measure it? Any ideas?
Are we assuming that both waveforms are on the oscilloscope at the same time?
Well, yeah, like if I had these two, so this, on an oscilloscope, I could do that, right? I could get those two. So I would look at the two peaks, right? And I would look at the time shift between the two peaks, right? And just, so the top is the voltage, the bottom is the current there. I went into the steady state portion, right? So I went somewhere out here and looked at the voltage and current. So I didn't look at t equal to 0. I actually looked at the steady state piece. What I did was, and this was in Simulink that I did this, I looked at the time difference between the two and converted that to an angle and found that the delay was about 63 degrees, right? Which is what I would expect it to be for the problem that we just did. All right. So steady state's usually good. The part that you don't think about too much is the transient piece, right? Because generally speaking, you guys know these are dynamic systems. You learn that with Yahoo and then you forget about it, right? So what do we do with this? Let's say I did want to find that transient response. All right, so I've got the steady state there, but I want to figure out the transient response. Well, I know what it is. It's an exponential, right? But what do I not know in this? I have AE to the negative t over tau. What do I not know? Don't know that A value. I don't know the amplitude of that, guys. How do I figure that out? What do I need to know? Initial condition, right? So in this case, I said that I of 0 minus is equal to 0.2 amps. Now I said 0 minus, right? So the implication here is that at t equal to 0, some switch state or something here that we don't see change, right? From 0 minus to 0 plus, what's got to be true about the current in the inductor? It's going to be the same, right? So in other words, I can say that I of 0 is equal to 0.2. And that's equal to, what do I do with this whole thing here? AE to the negative T over tau. What do I do with all that stuff to solve for A? Well, it's just a math problem to me now. I basically just say, okay, well, I plug in T equal to 0 into that thing, right? At some level, the inductor is behaving like an open circuit. No, I don't want to think too hard about that. I'm going to blow some brains away if I do. But if I just plug in T equal to 0 into that math, right? So if I have E to the 0 over tau, what's that? 1. Just, well, yeah, A times 1, right? So it'd be A plus, what do I do with this 0.0403 business? 0.0403 cosine what? Minus 63.43 degrees. Okay. So I get that whole business, and then I solve for whatever A is, which I didn't feel like doing. If I go through it, it becomes 0.182. All right. So if everything goes right, if I actually looked at this on the oscilloscope, what should it look like? Well, it should decay downward. At T equal to 0, what should the current be equal to? Should be equal to 0.2, right? So if I look at this, the black thing is always hard to see with you guys. That's 0.2 right there. It's really hard for you guys to see it, unfortunately. You'll see it, you can see it more clearly in the notes that are on. All right. So what's happening? What's the transient represent? Well, it's a transient thing that goes away. What's it represent physically? Change. It's basically the opposition to change that the inductor has. The inductor wants to keep his current constant, and he can't immediately change. He sort of slowly adjusts to the new steady state. These things spend their lives in steady state, but whenever you force a transient, whenever you force some new thing to happen by changing switches or whatever, it has to slowly adjust, and that's basically what's happening. Yeah.
So what is the importance of knowing the transient of children?
Most of the time you're in steady state, and so it doesn't matter, right? Where would it matter? Well, like the problem I gave you on the homework is a situation like what happens if all of a sudden I got a thunderstorm going through and everything's kind of sort of in steady state and a tree falls on the line, right? There's a transient that's going to happen there, and I got a circuit breaker that has to detect that and figure all that stuff out. That would be a situation where I need to worry about the transient, because that's going to cause, what's going to happen is the current's going to get bigger or smaller, and there's going to be some transition. This behavior where it's not sinusoidal is really kind of bad for a circuit breaker. That's one area. Another area you might think of is when I have a motor, for instance. Let's say I have a motor that's 100 horsepower, right? That motor is going to draw about 100 amps when it's in steady state. It's going to draw about 700 amps when it's starting up, right? And so I worry about those kind of transient behaviors to figure out what's that going to do to the voltages all throughout the grid and things like that. So we'll talk about situations where we need that, but usually it's, you know, we concern ourselves oftentimes with, like in protection, like we think about transients that might happen as the protection system needs to operate. We think about situations where we have to start equipment, starting pumps and starting fans and stuff like that in a power system. We worry about those behaviors. Those are the things that cause lots of problems, usually. But, you know, most of the time the system's just in steady state and we don't worry about it too much. And that's not really a thing anybody ever talks about with electronics, which is why you haven't really thought about it for too long. It is something that matters, though, quite a bit in terms of the way a grid operates, let's say. Good question. All right. Now, you will see, and I'll do a situation like this. You know, normally in the MATLAB stuff, in the homework, you guys will have a problem, and it'll be looking for specific variables. I solved through this whole problem, basically, using MATLAB, right? And so you can go through my code later. Again, I will post a video where I kind of walk through this with an example so you guys can see how to enter stuff in. All right. Okay, I'm going to pause for a second. All right, single phase power is what I'm talking about. So what does single phase mean? One power source coming in. Now, is that what you have in your house? What do you have in your house? You do not have three phase in your house. Gotta ask. Okay, you have two phases actually coming into your house. All right. But it's kind of sort of one. All right. So in this building, what do we have? Here we have three phase for sure. All right. Commercially, you always have three phase. Residential, you have single phase. And that single phase is kind of weird. It's actually what we call split phase. All right. So that was not. Hang on. Yeah. All right. So what we actually get in a house is 240 volts. Okay. And your house is wired kind of like this. This is kind of a weird one-line diagram, but this is sort of what it would look like. All right. What I have is two voltage sources that are 120. Now, they're RMS here, right? I'm going to use RMS for all these things. All right. One of them has an angle of 0 and one of them has an angle of 180, right? So that means when one of them is peaking, the other one's got a negative peak, right? So if I took the voltage between those two, what would it be? If you did the math, it would be basically 120 minus 120 angle 180 would be 240 angle 0. All right. And so you may have heard 120, 240. All right. So if you look at your house, you got some loads like your air conditioner that are going to be hooked up to 240. All right. What else is hooked up to 240? Dryer. Yeah, will be. That's really it, usually. Maybe an oven or a hot water heater, right? Stuff that's got giant resistors in it, all right? That's trying to heat up a lot of stuff. That's where you're going to have it. All right. Most of your outlets, like these guys, are hooked up to one of the two 120s. One of the two, all right? So you could, some of them, you don't know this, but they're 180 degrees out of phase. It doesn't matter to your computer or whatever when you plug it in, but that's what you got. All right, so that's what a single phase system would look like. All right, now in general, what they try to do is quote unquote balance the load across those phases. So there should be as many amps on each of the two phases. All right, and that's the way the whole grid is designed. All right, we get into three phase, they try to design everything so the same number of amps are on each phase. You can't guarantee that because the number of amps at any given time is dependent on what everybody's doing, right? But they try to make it that way. Okay? Now, so I would see something like this, and I always find it important to get some sense of what I'm looking at here. So if I go to an appliance, you guys have that three-phase outlet or single-phase outlet that you look at home. All right, you can look at this later, but basically, if you ever look at it, there's three prongs: the big prong and the little prong, and then the middle one. The middle one is ground. All right. The big one is what I call the neutral, and the little one is what I call the quote unquote hot. All right. The big one is the one that's always connected to 0 volts. All right. So anyway, it's important. I feel like it's important to have that sense of what's actually there. Right. That's kind of how we connect things up typically. In the ground, there shouldn't be any current going through it. All right. That ground is there to just ground the case of the device. All right. If there's ever current going through the ground, oftentimes you, like in your bathroom or your kitchen, you have those GFI circuits, right? What's GFI? Yeah, ground fault interrupt. Basically, if there's it measures the current going through that ground wire. And it says, hey, if there's any current going through that ground wire, there shouldn't be because it's not part of the circuit. It makes the assumption that if anything's going through there, it's going through your body, which is connected to the ground. And so it interrupts to do that. Right, so in a kitchen or a bathroom, there might be water on the floor, is their assumption, and so you are more likely to be grounded in that scenario. All right, Anyway, that's what that is. We can talk about all kinds of electrical stuff like that, but that's an important concept. All right, so I want to get into this definition of power. All right, so without me throwing that out there, what is the definition of power? You're going to say V times I, probably. All right, electrically it is V times I, but what is the definition of power? If I said, what does it mean to have power? What is it? Somebody said something. Yeah, it's work over time. It's the rate at which energy is being used. All right. So actually, you don't, if you've ever looked at an electric bill at home, you get charged for energy. All right. When you look at a commercial or industrial bill, you get charged for two things. You get charged for what's called demand and consumption. All right. So demand and power, we use those terms interchangeably. Demand is the rate that you're using energy, and energy is what you consume over time. All right. So if I said right now this building was using 1 megawatt, that means that right now it's converting energy. It's doing energy conversion at a rate of 1 megajoule per second. All right. So power is a rate, right? So the way I wrote this, basically, change in work over change in time. Work and energy are the same thing. All right. Now we use the passive sign convention. We talked about that. All right. If I do V times I, I get what I call P of T. What is P of T? You probably didn't think about that for more than a couple of seconds in circuits 2. What is P of T? Well, it's energy over time. P of T is instantaneous power. It's the power at any given instant in time. Okay. Now, what this says is P of T, in other words, how would I compute it? I would take whatever the voltage is, so V cosine whatever, I of T, I cosine whatever, multiply those together is what I would do. And I would get P of T. All right, we're going to look at what that looks like, but essentially that is something that can be positive or it can be negative. All right, what I'm saying here is if it's positive, I'm absorbing energy. So if my load here has a positive P of T, there is power flowing into that load. If that has a negative P of T, then energy is being sourced out of it. Okay. Can a load ever source energy? It can, if it's got energy storage, right? So if I had a source, that should be all a source ever does, hopefully. Right? If I have a load, it's only going to always absorb energy if it's a what? What does this load have to be to always absorb energy? A resistor. It has to be a resistor. All right? So if I have some inductance or capacitance, this guy's going to be also sourcing some energy from time to time. That's what Q represents. You guys remember P and Q? Yeah. Right? Q represents the fact that this guy has energy storage inside of it. Okay. All right. So if I actually went through that process, all right, and I went through and I calculated. So in this case, what I did was say, let's assume that V of T is equal to V peak cosine omega T, and with some angle, I guess, angle V. And let's say I of T was equal to I peak cosine omega T plus phi I. If what I did was I put those things together and multiplied them. So P of T, this guy here is actually whatever my V of T is times I of T. I don't want to go through I don't care about the details of this math, right? This is the result of it. All right. If I look at this, that term is constant. This one varies with time. That one varies with time. We make the definition, right, that this constant there, we call it P. All right, this constant here is the same as that one. This thing here we call Q. All right. What they are is they're related to the energy used and the energy stored. All right. So I'm being nerdy here. So P of T equals V of T times I of T. It's telling me how power is used as a function of time. Capital P, what I wrote right here, is a constant. What is that? Capital P. What is that? I wrote it there. I guess it's the real power, right? What's the real power? It's the word, right? What is the real power? Sometimes I call it the active power. The other term I use for it often is the average power. It's the average rate at which energy is converted from electrical to whatever. It's about a light bulb that was 60 watts, right? P would be 60 watts. Okay. And that would be the rate at which energy is being converted from electrical energy to light and heat, right? It's being converted at a rate of 60 watts. Okay. We're going to talk a lot more later on about this idea of energy conversion, because that's really what this class is about. Basically, 60 watts is the rate at which that electrical energy is becoming light and heat. Okay. So this guy, if I really wanted to get nerdy on it, I could say it's the average. So it would be the integral over a period of that P of T. That's the definition of an average. Okay. Now I use that because I want to look at a couple of different cases here, right? So let's say I've got a load that has a magnitude of 144 ohms. All right. It's going to be either in one case a resistor, in one case an inductor, and in one case an R and an L in series with each other. Okay. So without going too far, right? So in the case of a resistor, what should be true about the voltage and the current if I have a pure resistor of 144 ohms? What's that? How do they look? What's their phase relative to each other? Their phase shift is 0. All right, their phase shift is 0. Should there be any Q for this guy? There should be no Q. If you don't remember what Q is, the formula and everything, the pure resistor, hopefully you know that there should be no Q, right? This guy is pure, so the phi V minus phi I, the phase shift should be 0 degrees. This guy is doing what I would call pure work, right? I'm just converting energy from electrical to some other form. What if I have a pure inductor? What should be true then? What's true about the phase shift in that case between current and voltage? It's going to be 90 degrees. I'm not even going to worry about which way. Let's just say it's a 90-degree shift one way or the other, right? And in this case, am I doing any work? All of the energy that's coming out of the voltage source is basically just getting stored in a magnetic field. It's not doing any real work, right? So in this case, I have just energy storage. What about the third case, R and L in series? I got a little bit of both, and the phase shift should be somewhere between 0 and 90 degrees, depending on what the R and the L are. Okay, so what I want to do is I want to look at this and say, all right, what's going to happen in these different cases? So let's say if I have a pure resistor, what should be the angle of this impedance here? 0 degrees. All right, so this would be 0.833 amps with an angle of 0 degrees. Okay, so if I did the calculations here, what am I going to get for this? So I did this, if I go through the math, I did this for a 100-watt light bulb. All right, so essentially V peak times I peak. What about this cosine phi V minus phi I? The only part I'll ask you to compute. Cosine of this minus this, what's that equal to? 1. Phi V and phi I are the same here, right? So this guy, if I do the math, this guy is going to be 100 plus 100 cosine 2 omega t plus 0 sine 2 omega t. Right? And what's that going to look like? The reason why I wanted to look at this, and only look at this briefly, we're not going to do a lot of calculations with this, but I want to just understand it. So at the top, I got the voltage. In the middle, I got the current. What do I notice about those two things? They're in phase with each other. Here's the P of T, right? So I want to look at just a couple of things about this P of T. This guy is a pure resistor, so he's always absorbing energy. So what do you say? He's always absorbing energy. P of T should always be what? Positive or negative? Positive. If I look at this, for all the time that I've shown here, P of T is positive, right? The 0 line is right there, right? So it's always positive. What do you notice about that P of T? It has a frequency that's different than the current and the voltage, right? fact, what is that frequency? What is it? Double. Yeah, it's twice, right? And that's there in the math, right? 2 omega t. If my voltage has had a frequency of omega, that's got 2 omega. How can you look at that picture and know that it's twice? If I look at one period of the voltage or the current, I've got 2 periods of this P of t. Now, again, what's this red line or orange line or whatever that is that's in the middle? Right? Well, that's the average. If I look at the average, it's 100, right? That's the average power that's drawn, all right? Now, why did I do this, right? I mean, we're not going to do a lot of problems where we start doing a bunch of trigonometry, all right? I promise we're not. Why did I do this? Well, because if I have a single phase system like I have here, right? What I have happening is when I look at the power is always quote unquote pulsating. It's got an average, but it pulsates up and down. That's what I call this behavior here, where it's going up and down like this, where it's got this variation. I call that a pulsation in power. We'll talk about this when we start getting into 3-phase at the end of next week. But if I have a 3-phase system, what I end up doing is each of the phases has pulsations that when I add them together, go away. So a 3-phase load at 100 watts draws 100 watts. Its average and its power as a function of time is the same. All right, that turns out to be, if I'm building a motor or something like that, really nice on the motor. Motors don't like this pulsation. Okay, what's the biggest motor in your house? Air conditioner, and I don't know how many horsepower it is, but it's probably like 2, right? It's not very big. Okay, if I had a 100 horsepower motor, the bearings would fail pretty quick with this sort of thing. All right. All right, we don't see this nowadays. There's some really cool stuff going on nowadays for farms and stuff like that, where they're building some really big ones, but it's pretty uncommon still to see anything bigger than 5 horsepower. All right, for this reason. All right. So I don't want to get too much into this, but what would it look like if I had the inductor? What would this P of t look like for the inductor? What's the average power for the inductor? 0, right? So how would this look? So what I showed here was the average, right? The average was 100 watts for this load. If it was for inductor, it'd be centered around 0, right? So if I do this for the inductor, it is, right? What I see is that for the inductor, what's it mean when it's positive versus when it's negative? What's it mean for P of t to be positive? It's absorbing energy. What's it mean for it to be negative? It's sourcing that energy. That makes sense because what an inductor is doing is what? It's an energy storage device. So for half the cycle, basically for half the cycle, current is flowing into it to store energy. For the other half of the cycle, it's flowing out, right? But basically what it's doing is it's storing and then sourcing, storing and then sourcing, storing and sourcing. And on average, it's doing nothing, right? There's no energy conversion that's happening. It's just storing, right? But there is still a current that flows through the wires to make that energy storage happen. All right, so I'm not going to get too into the weeds on that. For this guy, it would be somewhere in between if it's an R and an L. All right, you can look at that stuff later. All right, what I did want to do is talk briefly about, all right, well, what happens if I'm looking at AC waveforms, right? And I'm looking at trying to compute the power. All right, so I'll talk later about why we do RMS. I'm going to skip over that for now. So what I want to do is I want to make sure that I touch on these, what I think you guys already know, right? So I talked previously about what is real power, what is reactive power. We have P and we have Q. Q represents the energy storage. I only have that if I have inductance and capacitance, right? What I have in here, couple of things that we need to remember. If I look at the P and Q definition, right? So P and Q, VRMS, IRMS times the cosine of an angle. Q is VRMS, IRMS times the sine of an angle. Angle V minus angle I. What is that? Angle V minus angle I. What is that? Gotta be something. Yeah, what's the angle of the voltage minus the angle of the current? And voltage and current are always related to each other. How? V equals what? I times Z. So that tells me if I go through this, phi V equals phi I plus phi Z. So what is phi Z? It's the angle of the voltage minus the angle of the current. So I can say that this is VRMS, IRMS, cosine phi Z, right? And this guy is VRMS, IRMS, sine phi Z. That tells me that P and Q are two parts of a vector, right? With an angle of phi Z. So in other words, we can write this as VRMS, IRMS, with an angle of phi Z, is how we can write a vector with those two things. And we call that vector S, right? The complex power. Hopefully you guys remember that, right? If I look at this carefully, because of the way those are set up, what we also said is that this is the same thing as what times what. See if you guys remember that. Two other vectors that multiply each other. Should be V times I, right? Power should be V times I. Sort of. I conjugate. V times I conjugate. Why I conjugate? Because it's voltage magnitude times current magnitude. And the angle is the angle of V minus the angle of I. I get the negative sign from doing the conjugate, right? This is basically, this isn't a proof. This is like somebody saw this and was like, oh, wow, that's cool. I could do that, right? There's not a derivation to why it's the conjugate, right? So what we call this sometimes is sort of the power triangle. And we give some names to this guy, right? So the magnitude of S, which is VRMS, IRMS, we call the apparent power. All right. And we call this the power triangle, right? So this is my real axis here. This is my imaginary axis. The real part's always P, the imaginary part's always Q. And this guy is S. Okay. All right. So if I go through this, right, we talk about complex power, right? I'm going to go straight to the summary that I have of all these things. So if you go through here, you'll see the summary of all this stuff, right? So what I do is I talk about a couple of different things. I talk about the apparent power, the real or active power P, the reactive power Q, and the power factor PF. Okay. You guys have seen all this stuff. It's been a while probably since you've used it, right? Apparent power, real power, and reactive power all have different units. Which one is, well, I guess I have it here. Which one is watts? The real power. That's the only one that's watts. They're all volts times amps, right? But we give them different names. All right. Why? There's reasons for that, right? This guy here we call volt amps. That's the apparent power. This guy here, the reactive power, we say has units of bars or volts, amps, reactive. All of them are volts times amps. We just give them a different name to be able to kind of differentiate between what they are. Right, all of these formulas here, I did them two different ways. One using RMS values and one using peak values. Now I'll address it, I guess, next Wednesday about why we use RMS. But one thing that's nice about this, you can kind of see it. What does it do to do RMS? Well, what people did was they said, I didn't need to remember this over 2 if I use an RMS value. It gets rid of that in all of these equations. That way, if I had a pure resistor, and I wanted to calculate the power in a pure resistor, it's still V times I, just like it is in a DC circuit. So sometimes we call that the effective DC value of that sinusoid, right, is the RMS value, because it allows us to compute power for a resistor by just still doing V times I. Whole reason why we do it. All right, so it turns out to be simpler to do the math that way. That's all. All right. All right. Now, this one last thing here, this power factor, right? The power factor is this thing that tells me what kind of phase shift there is between the voltage and the current. All right. Now, I mentioned that earlier there was a question about the angle of the impedance and what quadrants could I be in. I have that summary here. I say if I have an inductive load versus a capacitive load, an inductive load always has its impedance in the first quadrant. A capacitive load always has its impedance in the fourth quadrant. Right? If it was a pure inductor, what would the angle of the impedance be if it was a pure inductor?
Yeah.
It would be 90, right? If it was a resistor, it'd be 0. If it was a capacitor, it would be purely negative 90. So when I say inductive load or capacitive load, I mean there's some R plus L, right? And if it's capacitive, there's always some R plus C. There's no value of R that could ever push my real part negative. That's why I can't ever be in the second or third quadrant. All right, let's not think too hard about that part. All right. All of these formulas are what you'll need. Now, what we'll pick up with next time is we'll do some examples, all right, of how we do calculations with that stuff. It's pretty straightforward to do those calcs.